This section deals with the law of large numbers and the expected value. We're going to start with the expected value. The expected value really is a mean or an average. So it's just another way to say expected value is another way to say mean or an average. Average is another way to say mean. And really, it's again what you expect to get. You expect to get the center, you expect to get the mean, you expect to get that. And the way we calculate the expected value is you take, you're going to have a probability distribution or probability space, which will give you an x value and times that probability value. So the x is your outcomes, and the probability is the probability that goes with that outcome. And then you do that for every single one of them, and then add them all together, and that will get you what your expected value is. So again, each x is the values of a variable, and the p's are the values of the probabilities that go with them as percents. Actually, as decimals. You want to make them into decimals. So let's do an example. Let's say a single card is drawn from a deck. If you get an ace, you will win $12. If you get something other than an ace, you will lose $1.50. So then the question is, what is the expected value? So you've got two different options, and one thing that's useful here is to actually kind of make a little table with your x value and then your probability value. And your x value is what happens. So you could actually have a third column here, which is actually the outcome. And so your outcome is you get an ace, or you don't, or not an ace. And then if you get an ace, you win $12. So that's plus $12 because you get it. It comes to you. Your probability of getting an ace, well, there are 4 aces in a deck of cards, so 4 out of 52. If you don't get an ace, which is not an ace, so 4 out of 52 is your probability of getting an ace, your probability of not getting an ace would be 48 out of 52 because you do 1 minus, because it's a complement. It's not always the complement when you do expected value, but in this case it's the complement. And if you get that, you lose $1.50, which means you lose, means it goes away from you. So going away from you is negative. So positive is because it comes to you, so you positive $12 and minus 150. And then you just multiply the 12 times the 4 out of 52, and you multiply the negative 150 times the 48 out of 52, and you add them together. Notice your answer is negative 46. And that means that if you play this game and have this game you're going to play, you expect to lose, because it's negative, lose on average 46 cents per game. So you can either write the 46 cents this way or write it as 46 cents. Remember, you don't put the decimal when you do 46 cents this way. And that tells you kind of how much you're going to lose. Now, the question is this game fair? And a fair game, either way, some people think a fair game is because you get a positive expected value, but that means somebody loses. If you get a positive expected value, whoever you're playing against lost. So a fair game is one where your expected value is 0. It means nobody wins, nobody loses, everybody gets the same. Since this has a negative expected value and not a 0 expected value, then the game is not fair. So, let's do another example. So let's look at how many visitors do you expect to get in a zoo in 1 year. If your weather is sunny, you expect to get 4,000 visitors. If you're cloudy, you expect to get 3,000 videos. If it's rainy, you get 1,500 visitors. And if it's snowy, you only get 100 visitors. And then you can look up the percent of days with this kind of weather. So wherever this is, there's 47% of the days are sunny. 27% of them are cloudy. 19% are rainy. And 7% are snowy. So you want to find the expected value or the average number of visitors on any given day. So what you're going to do is you're going to take the 4,000, which is how many you expect to get, times the 47%, which you changed to a decimal. The 3,000 times the 0.27, which you changed to a decimal. The 1,500 times 0.19. and then 100 times 0.07. You're going to multiply those numbers together, then add them up, and whatever number you get is what you expect to get. So you expect to get, on average, 2982 visitors every day. So what that tells you is kind of, if you know how many you expect to get, then that can tell you, okay, I need to have this many employees because I kind of expect on any given day I need to have this many people available to help out all those visitors. Another thing to talk about is this idea of the law of large numbers, which gets us to kind of a concept called the house's edge. And if you ever play or do any kind of gambling, you will notice that the house actually will win. That's why casinos are so big and so luxurious, is because they actually are winning. And that's because they have what we call a house's edge, which is the amount the house can expect to earn for each bet. So in the previous example, the game that we were playing is you lost 46 cents, which means the house expects to gain 46 cents per game. So they get an idea of that, and that's how they can budget. There's also something called a Gamblers Fallacy, which is where this belief that if you have a string of bad luck, then that means you're due for a string of good luck. You've seen this if you ever watch people play slot machines. That one hasn't won yet. It will win this time because it hasn't won in a while. And that is a gambler's fallacy, and that keeps you gambling and keeps you helping out the house edge, by the way. But that also gives us the law of large numbers, which is that if you do an experiment more and more times, then your empirical probabilities, those experimental probabilities we calculated, will become or follow the theoretical probabilities. That doesn't mean that if you have an unfair coin and you flip it a bunch of times, you will get 50 out of 50. It means that if you have an unfair coin and you flip it a bunch of times, you will find out what that coin's probability is. So as an example, if you have rolled 2 dice and you add the numbers, then the probability of getting a sum of 2 is 1 out of 36, let's say. Probability of a 3 is 2 out of 36, and so forth. And if you were to plot those up, you could actually look and see that you would get this very nice, neat-looking distribution. In this case, with flipping coins or rolling dice, 7 is most popular, and then 6, 5, 4, 3, 2, 1 drops off. So we get this nice-looking symmetric distribution. And if you would actually roll dice that are fair, this is kind of what you would see. If you rolled loaded dice, then you might not see that. In fact, you might see a 2 come up way more often than, let's say, any of the other numbers. So if you got a distribution like this when you were doing your experimental probabilities, and you did it enough times, you would notice that, hey, 2 comes up way more often than it should, and this is what this dice looks like, which tells you, hey, this is a loaded die and not a fair die. So that's kind of what the law of large numbers is used for, is that if you want to know if something actually is fair and follows what we think should happen, then you actually can do the experiment over and over and over again, and then you'll see what that probabilities would be really, and then you can see, do they actually match it? So you can tell if something's fair or not.